Hello again, this is Professor Roman. Let's continue the group theory lectures. Now, I said at the beginning of this series that I wasn't going to do any applications of group theory, that this was a book on pure theoretical group theory. Well, I didn't exactly lie, but I did include this chapter on applications of groups in mathematics. It's not very detailed. It's just meant to be a little bit of an overview. So let's talk about that now. Groups do have many uses within various branches of mathematics, such as geometry, analysis, algebraic topology, number theory, coding theory, cryptology, just to name a few. Of course, they also have wide application in other areas of abstract algebra, ring theory and field theory. In fact, one of the prime motivations for the discovery of groups came from its use in helping to understand the nature of roots of polynomial equations. Group theory is also very useful in the sciences, such as physics, chemistry, computer science, even music theory. Well, it's not terribly useful in music theory, but it does occur. Some people do use groups in their study of music theory. As far as computer science is concerned, I once, many years ago, sat in on a class in Internet security, and the professor spent several days, perhaps a week, describing the rudiments of groups and group theory to the students. I sat there thinking, this is so superficial and it's going so rapidly that I didn't think any of the students would get anything out of it. But nonetheless, the professor must have thought that it was important to introduce group theory to the students in a course on Internet security. So let's take a quick look at some of the uses of group theory in other branches of mathematics. We'll start with groups in geometry. The concept of symmetry plays a key role in geometry and in the study of nature. There's symmetry everywhere in nature. Just how does one describe the symmetries, for example, for a regular pentagon? That's shown in this picture here. Well, as we briefly discussed for the square earlier, when we were talking about examples of groups, the situation applies analogously to other regular polygons. So in this case, it's clear, for example, that reflection about the vertical axis is a symmetry of the pentagon. I'll call that reflection sigma. Also, a one-click rotation, say clockwise, so 72-degree rotation, is a symmetry of the pentagon. It'll send vertex 1 to this location at vertex 2 and so on. So it sends the pentagon to itself. It's possible to show, and we will do so later on when we look at the dihedral groups in earnest, that all symmetries of the regular pentagon are obtained by taking products, that is to say compositions, of the reflection sigma and this rotation, which I'll call rho. In other words, the symmetries of the regular pentagon are described by the dihedral group D10. generated by rho and sigma. Now, I haven't defined what it means to say a group is generated by a set of elements, but we're going to do that in the next chapter. And the notation here, D10, reflects the fact that this group has order 10. As I mentioned for the dihedral group of the square, some authors will write this as D5 because the pentagon has 5 vertices. In any case, dihedral groups are used to describe symmetries of regular polygons of any size. And it's not hard to believe that other groups describe symmetries in other geometric or physical contexts. Unlike the other topics I'm going to discuss briefly here, this topic of dihedral groups we will study in considerable detail. Let's look at groups in analysis. Topological groups are groups for which the group operations are continuous. So there needs to be a setting in which continuity can be defined. That's a topological setting. As a simple example, the real numbers R with the usual distance function, it's called a metric, are a topological space. They're a metric space, this set. And it is a topological group under addition, because if we have two convergent sequences of real numbers, say xn converges to x and yn converges to y, then the sequence negative xn converges to negative x. So this is telling us that the function that takes the negative of a real number, that unary operation, is continuous. It preserves limits. And also xn plus yn converges to x plus y. So this tells us that the binary operation, the function from r cross r to r, also preserves limits. More generally, n-dimensional Euclidean space Rn is a topological group under addition. The general linear group, and these are the invertible n by n real matrices, this is a topological group under addition when we think of it as belonging to this Euclidean space. This is r to the n squared, and n times n. Now the interplay between the algebraic structure and the continuity structure in a topological group provides a very rich and powerful setting for topological groups. And that's all we can really say now, because I'm not going to assume you're familiar with topology, and we'll end this example here, except to say that this structure can enable mathematicians to do various types of analysis, such as Fourier analysis, on groups, on topological groups. Topological groups have applications in theoretical physics, for example, such as in the derivation of conservation laws. How about groups in algebraic topology? Don't be frightened off here. You don't need to know anything about algebraic topology to follow this in general terms. Homotopy groups are used to classify surfaces, or more generally, topological spaces. The simplest example of a homotopy group is called the fundamental group of a surface. and it describes the number of holes in the surface. So let's look at an example. Consider these illustrations here. On the left, we have two continuous curves. They're denoted by the thick lines. So the outer curve is this one, and the inner curve is this one here. I called them C1 and C2. These curves pass through a fixed point called the base point. So they're anchored there. Now, each of these two curves can be continuously transformed into the other curve. And by that, I mean they can be transformed one to the other without breaking the curves or changing the intersection point of the curves with the base point. That's an anchor. That stays fixed. And I've shown some intermediate stages of that deformation here, just 3 of them. But it's a continuous deformation. If I put them all in, I just have to make the whole thing shaded. You can think of the curves C1 and C2 as made of string, and the base point as an eyelet. And basically, you take one of the ends of the string and you pull it through the eyelet, and it will start to move in a continuous fashion, and it is, at least theoretically, possible to transform C1 into C2. To get from C1 to C2 to C1, you'd have to push the string. Okay. Continuous transformations of curves with a fixed base point is called homotopy. And two curves are homotopic relative to the base point if each curve can be continuously transformed into the other without changing the base point. Homotopy is an equivalence relation, and the equivalence classes are called homotopy classes. Now, it's possible to define a binary product on continuous curves with a fixed base point. For example, to compute the product C1, C2 of the curves in this figure, we start at the base point, follow curve C1 until we return to the base point, and then follow curve C2. Again, returning to the base point. This composition produces another continuous curve anchored at the base point. Now, I'm fudging a little bit here. We have to be a little more careful in the definition here, but we don't need to go into the precise details because it's not important. We're just trying to get a sense of what's going on here. Homotopy is an equivalence relation on the curves at a base point. And I'll denote it by a squiggly line. Then it's the case that if C1 and C2 are homotopic, and D1 and D2 are homotopic, then the product C1, D1, and C2, D2, in that order, those are homotopic. I said C1, D1 because that's the order in which you apply you follow the curves. The product, I guess, should be red, D1, C1. Okay. So if I use this notation, square bracket C, to denote the homotopy class that contains the curve C, then we can get a well-defined product of homotopy classes by setting this. So the homotopy class containing D times the homotopy class containing C is equal to the homotopy class containing DC. The point of this previous discussion here is that it is the reason that this is well defined. Doesn't matter which representatives you choose from each homotopy class, you will get the same homotopy class on the right side here. The resulting product makes the family, which I call script H, of homotopy classes anchored at a fixed base point into a group. It's a group product, and it's called the fundamental group of the surface at the given base point. I'd like to keep this figure on hand here as we talk further. I wish I had a bigger screen, a bigger camera, but let's see what I can do here. So here's the figure, and okay. Now this figure in the middle here shows a surface with a single hole. So the shaded portion is the surface. It's a donut. It's more or less a torus, or it could be a flat surface, could be three-dimensional. It doesn't matter. Call it a donut or an annulus. The curve X in the figure belongs to the homotopy class that contains all continuous curves through the base point that loop around the hole. You can continuously deform X, but you're just going to get another loop fixed at the base point, looping around the hole. What about X squared? X squared, could it be homotopic to X? Well, if so, then remember X squared is start at the base point, go around X twice. If that was homotopic to X, we could deform X squared into X, but X squared wraps around the hole twice, X wraps around only once. So some thought should convince you that this can't be done. You can't deform X squared into X. Another way to think of it is to imagine wrapping a loop of string around an infinitely long pole twice. Wrap it around twice, and then try to deform that into a loop that goes around only once without breaking the string. You can't do it. So X squared is not homotopic to X, and therefore the homotopy class containing X squared is different from the homotopy class containing X. As a matter of fact, for all integers k, the homotopy classes containing X to the k are distinct. Okay. If k is negative, then X to the a negative exponent is go around the loop in the opposite direction, however many times the absolute value of the exponent tells you to do. Okay. So we can think of a word over this alphabet, XX inverse, as a member of the fundamental group. Even though it's really the homotopy class of that word that's the true member of the fundamental group, it's common to just take a single element from the homotopy class and call that a member of the fundamental group. Now, the only algebraic relations that exist between members of this fundamental group are the ones that come from these two relations. XX inverse is homotopic to 1. If you travel around X, then reverse and go around X again, you haven't gone anywhere. Well, you can probably guess now what's going on. The fundamental group of the single hole surface in this picture is just the infinite cyclic group generated by X, or the free group on X. It's just the same thing. Now the right side of this figure shows a surface with two holes. In this case, the homotopy classes containing x to the k and those containing y to the k for all integers k are distinct, as are the homotopy classes such as the one containing xy, yx, or something like this, x squared y to the negative 3x, and so on. In fact, the fundamental group of the two-hole surface is the free group on the two symbols x and y. So groups can be used to describe the number of holes in a surface. Incidentally, it might seem at first that all fundamental groups are free groups, but that's not the case. For example, the fundamental group of a torus is an abelian group. It's Z direct sum of Z with itself. It's this direct product, but it's additive, so we call it a direct sum. Let's talk now about how groups appear in a branch of mathematics known as coding theory. This branch of mathematics is devoted to the encoding of what is called source data, such as text messages, images, things like universal product codes that appear on every package in the grocery store, credit card numbers, and so on, for the purpose of detecting and even correcting errors in either the transmission or the storage of the data. I'll generally speak in terms of transmission. Group theory plays a very significant role in coding theory. To understand the issues involved, suppose that we want to encode a source message. Let's say a text message such as, "The Ludendorff Bridge is still intact." And we want to send that over a secure communication line, something that might very well have been done during World War II. For encoding source data, we need to encode each source symbol. So for text messages, it would be letters, upper and lower case, punctuation, special symbols. Each source symbol needs to be encoded into a code word, which can then be transmitted, and at the other end can be decoded by the receiver. So we need sufficiently many code words to encode all the source symbols. And as an example, just say 64 code words for handling text. If we were transmitting images of, let's say, Jupiter or Mars from outer space, we want high color images, high resolution images. We might need millions of code words to do that. We'll assume that each code word is a binary string, since binary is much easier to transmit or store by digital means. And we'll also assume that all code words have the same length. Just as an aside, there are variable length codes where the code words have varying lengths. They're designed primarily for efficient transmission of data. If your transmission lines are restricted in bandwidth or your storage is restricted in capacity, then these things come into play. But that's really a separate issue. So we'll stick with what are called fixed length codes, where every code word has the same length. So in our example, to get 64 code words, each code word has to have length 6. And for example, if a code word such as 100100 is sent over a communication line, then a bit error could result in this word being received, 110100. So the bit in the second position was altered in transmission. And the same thing would apply to storage. So we have here a bit error in position 2. A binary code of length n and size m is a set C consisting of m binary strings or binary words. They're called code words, each of which has length n. So the accepted notation for that is nm code. So the length of the code words comes first, the length of the code, and the size of the code comes second. So let's assume that C is an NM code. If the receiver of an encoded message of a code word, let's say, receives the binary string R, what happens? Well, if R is a code word, if the received word is a code word, then the receiver is going to assume that no errors occurred, which is generally going to be the case, hopefully, and simply decode R as that to recover the source symbol. That's a code word, so they can decode it. And the reason that the receiver would do that is because there's no way to tell just by looking at the code word R whether it was the code word that was sent or not. So the code word gets so it gets decoded, assuming there was no error. Now, of course, that's not necessarily the case. It's possible that enough errors occurred to change the code word that was sent into a different code word that is then received. And again, the receiver is going to do the same thing and decode that code word and assume there were no errors, and that would be incorrect. So this is not an infallible process. The idea is to make it as likely as possible that we can correct any errors. But what do we do if the received word R is not a code word? Well, it's reasonable to assume that bit errors have a relatively low probability of occurrence. Let's just say the probability of a bit error is 1/1000th. So one out of every 1,000 bits gets scrambled. We also will assume that the bit error events are independent. That is, the event that a particular bit undergoes an error does not affect the probability that any other bit will undergo a bit error. Now, that is not very realistic. If you think about, say, transmitting data over a phone line, if there's an electrical glitch of some kind, it's quite likely or quite possible that it will affect multiple consecutive or nearby bits. So this is a simplifying assumption that's not necessarily very realistic, but without it, life becomes a whole lot more complicated. So under these assumptions, bit error of 1/1000th and independent errors, the probability that 2-bit errors will occur is p squared, which is 1/1,000,000th. So it's much more likely that if there are any errors, there'll just be one error. That the probability of more than one error is much less than the probability of one error. So it makes sense to decode the received word that is the code word that is closest to the received word, in the sense of having the fewest number of bit differences, because that's the most likely scenario. So this leads to the following concept. Let x and y be binary strings of length n. The Hamming distance from x to y, denoted by rho of xy, use that, is the number of bit positions in which x and y differ. So for example, the Hamming distance between this code word that we spoke about earlier and the received word is 1, because there's a bit error only in the second position. It's not hard to show that Hamming distance is a metric, and so a binary code is actually a metric space. So in particular, we have reflexivity, we have symmetry, and we have the triangle inequality, which I'll let you prove if you're interested. So taking advantage of this metric structure, we can now state the main principle for decoding. Let C be a binary NM code. Decoding a received string R as a code word C that has minimum Hamming distance from R, so this is what it looks like in symbols, is called minimum distance decoding, or nearest neighbor decoding. Actually, nearest neighbor decoding results in replacing the received word with a code word that has greatest probability of having been sent. So it makes perfect sense. And for that reason, nearest neighbor decoding is an example of what's called maximum likelihood decoding. Now I should emphasize that minimum distance decoding is not infallible, and there are actually two problems that can occur. First, one or more bit errors could actually place the received word closer to the wrong code word, the code word that was not sent, and then the received word would be corrected incorrectly. You would assume that the wrong code word was in fact sent and misinterpret the data. The other problem is that there might be more than one code word at minimum distance from the received word, and then you have an ambiguity problem. Which one do you pick? To mitigate these problems, it would be best if the code words themselves were not too close to each other, separated as far as possible from each other, to give more space between the code words. And that would be, of course, in the sense of the Hamming distance. So here's the definition. The minimum distance, delta, of a binary NM code is the minimum distance between all pairs of distinct code words. And a code with minimum distance delta is called an NM delta code. So these are the parameters of the code: code word length, number of code words or size of the code, minimum distance of the code. These are the three key parameters of a binary code, or any code actually, but most codes are binary. if C is an NM delta code, then the triangle quality inequality guarantees that there is at most one code word within distance less than delta over 2 from any received word. So the received word R comes in, there's at most one code word within distance less than delta over 2. That will remove the ambiguity problem. And here's the reason. It's a triangle inequality. I'll let you sort that out. Okay, so just as an example, an NM3 code that has minimum distance 3 is then capable of correcting any single bit error. But that is assuming only a single error did occur. If a single error occurred, then nearest neighbor decoding will correct that error, bring you to the correct code word, the code word that was actually sent. But of course, you don't know whether there was only a single error. So again, this is not an infallible process, but it's the most likely, it has the best outcome, most likely outcome. So for this reason, a code with minimum distance 3 is referred to as a single error correcting code. But, and this is a little bit of an aside here from our main goal, a code like this can be, and is in fact, double error detecting, because if either 1 or 2 bits occur, no more than 2, then the received word won't be a code word, and so the receiver will know instantly that some errors have occurred. But what's interesting about this situation is that these two options, single error correcting and double error detecting, are mutually exclusive. If the receiver decides to use nearest neighbor decoding on every received word in order to correct single errors, then double errors will not be detected. But instead, what will happen is that the received word will be incorrectly adjusted to, it'll be adjusted to the wrong code word. It'll be decoded incorrectly. So a choice has to be made up front. Do we do single error correcting, or do we do double error detecting? Can't do both at the same time. And in fact, when a code is used for error detection, in some cases, for example, in some cases of transmission of the data, the receiver might be able to request retransmission. So that could be the best of all worlds if that's possible. And you notice that probably when you go to the grocery store, as the checker's scanning your products, the scanner scanning the UPC, the Universal Product Code, the barcode. Sometimes you'll hear beeps, and then the checker that alerts the checker that an error was detected, and so the checker scans again, sometimes multiple times to stop the beeps. That's error detection rather than error correction, and it's useful in that situation because rescanning is all but trivial. If you've stored some data on a DVD and 10 years later you look at it and there's some garbage there, you've detected errors, but there's not much chance you can correct them in that situation. That's why you need backups. In any case, a well-designed code should have the following 3 properties. C must, in fact, have enough code words to encode all possible source messages. Second, the minimum distance of the code should be as large as possible to do the job. That will allow the maximum number of bit error corrections. And third, there should be an efficient algorithm for actually performing nearest neighbor decoding. Unfortunately, though, the first two goals, enough code words and far enough apart, are contradictory. The more code words you have, the closer they're going to have to be. And that's the main problem in designing error-correcting codes, at least of this nature. One of the most important types of codes are the linear codes, and that's partly because they're easy to decode. As you may know, the set Z2n, this is the set of all binary strings of length n, is a vector space over the field Z2, where addition is taken modulo 2. Multiplication, of course, is just multiplication by either 0 or 1. Scalar multiplication, I'm sorry. It is scalar multiplication by either 0 or 1. And that's trivial, scalar multiplication. Or put another way, linear combinations are just sums. Right? So Z2n is nothing more or less than an abelian group. The scalar multiplication is really sort of unnecessary. Addition takes care of scalar multiplication pretty much. A linear NM code is a subgroup of this abelian group, again under addition mod 2. So there's our connection between group theory and coding theory. Linear codes, binary linear codes, should have said that, a binary linear code is by definition a subgroup of this abelian group Z2n. Linear codes have relatively large size, or they can have relatively large size, and they can be very easy to decode. So that takes care of two of the three requirements for a good code. But they may very well suffer from low minimum distance disease. So that's a problem. For example, the most famous linear codes are the Hamming codes, discovered by Richard Hamming. There's one Hamming code, H sub r, for each positive integer r. And the Hamming code H sub r has these parameters. Its code word length is 2 to the r minus 1. Its size can be quite large, as you see here, 2 to the power 2 to the r minus 1, but they are all of them are minimum distance 3. So H sub r is very large in general, but is capable of correcting only a single bit error. So that's their main disadvantage, and quite a substantial disadvantage. H3, for example, code word length 7, size 16, minimum distance 3. This code is good for examples, but not much else, because you only can encode 16 different source letters. H4, code word length 15, 2048 code words. So this is enough for most non-image type source data, text data, and so on. H5 is a code that is quite large, 67 odd million code words. So that's probably suitable for encoding high quality images, but it has that serious disadvantage that it can only correct 1 bit error per code word. But to illustrate the decoding of a Hamming code word. I should close that up. For, let's say, the Hamming code H3, which, as I said before, is small enough to use for examples. Let's say we have this code word, 11010001. But, unknown to the receiver, an error occurs in transmission in the third position. So this 1 is incorrect, should have been a 0. The Hamming matrix, and there's a Hamming matrix associated to every Hamming code. The Hamming matrix looks like this for this particular code H3. The kth column here, read from top to bottom, is just the binary representation of the number k. So this is 1, 2, 3, 4, 5, 6, 7. Now, to decode the received word R, we write that received word as a single column and multiply it by the Hamming matrix, HR. And we use addition modulo 2, comes out to be this. This is called the syndrome of R. And lo and behold, if you read this top to bottom as a binary number 011, it's equal to decimal 3. That is the position of the bit error. So the syndrome tells you where the error occurred, and you can fix it. As our final application of group theory to mathematics, cryptology is the branch of mathematics that designs codes not for error detection or correction, but for secrecy, for hiding the information from unauthorized eyes. And here, even the cyclic groups have applications. So one model for a cryptographic system can be described as follows. Two persons, and they always seem to be named Alice and Bob for some reason, wish to communicate secretly over an insecure communications channel, like a mobile phone, for example. If Alice and Bob possess some common information that no one else knows, this is called a shared secret key, then they can use this key together with a cryptographic protocol that's known as symmetric key cipher to communicate securely. A symmetric key cipher is a cryptographic method that uses the same key for both the encoding and decoding of secret messages. And one such method is the Advanced Encryption Standard, AES, which has been adopted by the United States government, in fact, and is in use worldwide. However, if Alice and Bob do not share a secret key, then they can create one, even without being in direct communication with each other. And one method is known as the Diffie-Hellman Key Agreement Protocol. And it goes as follows. Let P be a prime number, and let G be ZP star, which, as we will see, is a cyclic group. I mentioned that earlier. I mentioned that it was rather difficult to show, but we will prove that this is the case. So let A be a generator of G. And suppose also that both A, the generator, and P, the prime, are public knowledge. Maybe they're printed in a newspaper, doesn't matter, and they're available for anyone to see. To create a shared private key, Alice and Bob can do the following. Alice chooses at random and uniformly an integer I in the range 2 to p minus 1. And she computes a to the I, so she takes the generator a and raises it to the ith power. And she makes that available to Bob, anyway, private or public. She can put that in the newspaper as well. Bob does the same thing. He chooses at random and uniformly an integer j in the range from 2 to p minus 1. And he computes a to the j, and he makes that available to Alice. He sends it to her either over a private or public method, doesn't matter. So a, p, a to the I, and a to the j are all public knowledge. Alice then takes a to the j and raises it to the ith power. Okay, she knows I, that was her choice, and she doesn't make I public, she makes a to the I public. And so she knows Bob's a to the j. He computed a to the j, he made it public, she knows it. She knows her private exponent I. Similarly, Bob does the opposite. He knows Alice's computation of a to the I. He doesn't know I, but he knows j because that's the integer he picked. So he can compute the same quantity in reverse. So this common value, which is a to the ij, we'll call it k, that is a shared secret key. The secrecy of the key depends upon the assumption that knowing a to the I and a to the j does not make it computationally feasible to compute a to the ij. That's the assumption here. But there are more complex variants of this model involving non-abelian groups that are designed to make the assumption more reasonable. So we're just dealing with this simple acyclic group ZP star. Okay. So that's just a brief look at how group theory enters into cryptology.